We're going to continue looking at multivariate probabilistic models, and specifically we're going to look next at probabilistic graphical models. So this is a topic we're going to look at a lot in this course. Probabilistic graphical models are a really powerful way of representing relationships and uncertainty and probabilistic distributions over collections of random variables. And in particular, let's look at a Bayesian network. Let's start with a specific example, which is the following network of random variables. Let's look at these 4 random variables: cloudy, sprinkler, rain, wet grass. These are all binary random variables, so cloudy, is it cloudy or not? Did the sprinkler run? Did it rain? And is the grass wet? So we define a Bayesian network. A Bayesian network is a way of representing conditional dependence and conditional independence among random variables. So we're going to draw an arrow from one variable to another if there's a conditional dependence from the parent to the child. So, for example, in this case, if it's cloudy, it's more likely to rain. So there's a conditional dependence there. If it's cloudy, perhaps the owner of the house is less likely to turn on the sprinkler. There's a conditional dependence there. And then that means that wet grass is a function of both sprinkler and rain. If either the sprinkler is turned on or it rained, then the grass is wet. Note that we don't draw an arrow from cloudy to wet grass because the clouds themselves don't cause the wet grass. It's just the rain and the sprinkler. So if we define a Bayesian network, we usually define a conditional distribution for each variable given its parents. That is, we get probability of cloudy, probability of rain given cloudy, probability of sprinkler given cloudy, and probability of wet grass given cloudy, given sprinkler and rain. So this is a Bayesian network form of defining a probabilistic distribution. This form is equivalent to giving a full joint distribution over our 4 variables. Here's how we can realize that. Probability over our 4 random variables, C, S, R, and W. We can apply the chain rule. We're going to apply the chain rule specifically in topological order of the variables. So what is topological order? So a Bayesian network is required to be a directed acyclic network, or directed acyclic graph rather, DAG. So it's a directed graph in the sense that it has edges, and those edges have directions, they're arrows. And it's required to be acyclic, which is to say that there can't be any directed cycle. So you couldn't go cloudy causes sprinkler, causes wet grass, causes cloudy. So that makes sense if these indicate conditional dependence, because basically for reasons of causality, like you can't have cloudy causing wet grass, which then goes back and causes cloudy. And it could be because of evaporation or whatever that wet grass yesterday causes cloudy the next day, but those 2 values, cloudy yesterday and cloudy tomorrow, those would be 2 different random variables. So there, you could have feedback loops over time, but at any given moment, there can't be any cycles of causality in a Bayesian network. That's why it makes sense that a Bayesian network should never have cycles in it. Okay, so now one mathematical property of DAGs, directed acyclic graphs, is that you can define an order on the nodes, or in this case variables, of a directed acyclic graph such that parents always come before children in the graph. And if you kind of think about that for a while, you can realize why that is. So one consequence of that is that there's always, in a DAG, there's always at least one variable that has no parents. So there's a topological ordering. That's a consequence of the Bayes network being a directed acyclic graph. Let's go back to trying to figure out what is the joint distribution over these variables. So if I wanted to write out the joint distribution, I can apply the chain rule, and I'm going to apply it, in this case, specifically in the directed acyclic graph topological order. I'm going to go from the end of the order to the beginning. So children for parents, probability of W given everything else, S R W times probability of sprinkler given R C, probability of R given C, probability of C. So all I did here was I applied chain rule going from in inverse topological order. So I first did the child, then did parent. So you'll notice here that there's never, it's always children there's never the parent in front of the condition and the child afterwards. I made a mistake here. This should be cloudy there. I think everything else I got right. Yep. Okay, so now we know the distribution of wet grass given sprinkler and rain, which means that we don't need C in the condition here. Same thing goes for this one. We don't need rain to define cloudy. Now notice that once we've done that, we get here exactly those conditional distributions that we had specified in our Bayesian network. Probability of W given S and R, probability of S given C, R given C, probability of C by itself. So that is to say that if I give you, and by the way, the reason we could cross these things out is because of the conditional dependence that we've specified in the Bayesian network. We know that C is independent of W given S and R. Once I give you these distributions, I can just multiply them all together like this to get my full joint distribution. So that's another way of saying that no matter what Bayesian network I give you, a Bayesian network is just another way of specifying a full joint distribution over the variables. So if what you really wanted was a joint distribution, that's fine. And I give you a Bayesian network, that's fine. You can just take all those distributions and multiply them together. Likewise, it's always possible to generate a Bayesian network from any distribution. It may not be a very useful Bayes network, but I could just apply the chain rule in any order, and I would just draw the variables in a chain with each one connected to all its parents. That's a perfectly valid Bayesian network for any set of variables. Okay, what if I don't know some of the parameters of my Bayesian network? What if I want to make a learning problem where I learn the parameters? One way to include this inside the Bayesian network is just to add the parameters as additional variables additional random variables or additional nodes in the Bayesian network. So let's say, as an example, I know that S somehow depends on C. Whether or not we turn on the sprinkler somehow depends on whether or not it's cloudy, but I don't know what that probability is. Let's call that probability PS. I could just say S depends on two things. It depends on whether or not it's cloudy, and it depends on PS. In this case, PS would be two values. We could write it like this, perhaps, even if we wanted to be really explicit. Given that it is cloudy, what's the probability of S? And given that it's not cloudy, what's the probability of S? So if I don't know what those values are, I can just put those as additional variables, and they're going to go as parents of S here. It's worth thinking a little bit and convincing yourself that they should be parents of S and not, let's say, parents of C. We think of them as sort of modifying this edge here. But the way to realize that they should be parents of S and not parents of C is that when you try to figure out what C is, you don't need to know what the probability of S is at all. But you do need to know those probabilities when you go to try to figure out what the value of S is. So you're going to need to know three things, these three things here. If we already know what the values are, one kind of convention of probabilistic models and Bayesian networks is that if a variable is unknown, we draw it with an empty circle. If a variable is known, we draw it as a shaded circle. I can't really draw shaded here, so I'll just use yellow to indicate that this is a variable that's known. Of course, in a real-life Bayesian network, some variables can be known sometimes and unknown other times. Often, when we approach a problem, one variable is always known, but we still want to reason about it. And sometimes a variable is always unknown. We want to try to do inference over it. So this is a convention when we're looking at Bayesian networks. Empty means unknown, shaded means known. So there could be either two options. One is that we already know what these variables are. That is, we have parameters, we know what the probability of sprinkler is given cloudy, or we could draw it as an empty circle indicating that we don't know what these probabilities are. We want to do inference in order to determine the values both of sprinkler, perhaps, and of the probability of sprinkler given not cloudy, for example. Here's a bit more notation that's relevant when it comes to probabilistic models. So it's very often that we have multiple copies of the same variable or multiple observations of the same variable. So it might be x1, x2, ... xn. Let's say perhaps they're all Gaussian distributed with the same mean mu. So in that case, we could draw it like this. That here is a way we could draw our probabilistic model. Some kind of syntactic sugar, that is to say, some way we can make it a little bit easier to look at, is with what's called plate notation. So here we have mu, there's just one mu, and then here we're going to write xn with a plate, indicating that there are multiple copies of x indexed by n. So we might write n equals 1 ... big N here to say that this n takes values 1 up to n. So there's n copies of x from 1 to big N. There's just one value mu, and each one is a parent of xn. So this is our kind of unrolled probabilistic model. Here's our probabilistic model in plate notation. You'll see something, so this is kind of the most explicit way of writing this. You'll see people write something even more succinct, which is to have instead just big N in the bottom right here of the plate. This is to say that there are n copies of this plate. You're sort of supposed to implicitly realize that this n applies to, you have n different copies of this variable. So you'll see this notation a lot. It can be there's sort of a lot of kind of inference you have to make to connect this, but usually it's pretty simple because usually you just have, in this case, n copies of the same variable, and it's pretty clear which variable we're talking about. So we're going to see plate notation a lot in this course, and you'll see it a lot in machine learning because it's very common that you have many observations of a variable that's distributed the same way. And in particular, the plates are often going to look like this, where you have many observations, and then there's some parameters that live outside the plate. You're going to be trying to infer these parameters, and you have just one copy of them that influence all of your observations. We're going to define one more type of probabilistic model, and that is a mixture model. So mixture models are going to come up a lot, especially when we come to clustering. So if we have a mixture model, we're imagining that our probabilistic density is just a mixture of some other densities that we've defined. So mixture models are also very useful if we want to kind of combine other distributions to get some kind of more complicated probabilistic distribution. So mixture models are defined like this. We want it to write the probability of some value y. We're going to define that using big K other distributions. Each one like this, defined as probability pk of y. So each one could be, perhaps it could be n different Gaussian distributions. Perhaps it could be n different categorical distributions, n different Bernoulli distributions, perhaps multiple distributions, maybe a Gaussian and a uniform distribution. Those could each be, we could have one Gaussian distribution and one uniform distribution, for example. We have one weight pi k per distribution. This is just a variable. It doesn't have anything to do with the circle constant. We're just using pi as a variable. And if we want to know what is the probability of a particular y, well, we just sum together the different probabilities according to each of these individual models that we're mixing together. An equivalent way of writing the same thing is that we imagine that we have some z that determines which cluster we're a part of, or which of the k models that we're a part of. So this is a value in 1 to k. Let's write that. Z is in 1 to k. And then that z determines the value of y according to this distribution here. So probability of z is a categorical distribution with these probabilities pi 1 up to big K. And the probability of y given a specific z equals to k, is just p of y using the distribution associated with k. We could write this equally well as pk of y. So that is to say that this thing equals this thing up here. So again, there are a couple places where this comes up. One is, as I said, maybe we're trying to make some kind of more complicated density some complicated density, and we're going to use components of other densities. A common one, for example, is, let's say that we think most of our values are concentrated around a given point or a given value. Let's say they're continuous. So maybe their heights, for example, we're collecting heights of people. We're trying to model somehow what that height is. We might use a Gaussian distribution around an average height, let's say 5 and a bit feet. We would use a Gaussian distribution to model that value. But maybe we're getting this from survey data, and maybe we find that people just like to put in random values to troll us. So maybe we want to say, okay, some part of the time we get an actual value, and that's going to come from a Gaussian distribution. Part of the other time we get a random value that's uniformly distributed from 0 to, let's say, 100. Maybe 100 is the highest. 100 feet. 100 feet is the highest value that our form lets people put in or something. So this can be kind of nice. So that would be a mixture model with two components. One is a Gaussian component, the other is a uniform component. It can be useful in kind of practical machine learning and data science to put in like a uniform term like this to kind of cover our bases. It stops seeing that 100 value in our data from like messing up our inference somehow. There's other ways you could deal with it, like some kind of outlier removal, but that's one way, to just add a mixture term to cover this weird stuff. Another case, again, where we see mixture models is some kind of clustering. So that is to say, we imagine that there are 5 types of people. We want to discover both what is the relative probability of each of those 5 types, and then what is the distribution over some kind of observations for the 5 types of people. So a classic example is k-means clustering. K-means clustering is a way of learning a Gaussian distribution, a mixture of Gaussian distributions. That is, we might learn 5 different Gaussian distributions that correspond to our 5 clusters of people or examples or whatever. One definition that can be useful when it comes to clustering specifically is we might want to know the following. What is the probability that Z, the cluster membership, equals a particular value given the observation? We're using notation for the textbook here. The textbook changed notation from y to x, so that's why you see an x here. So we want to know what's the probability that Zn equals k given x. That is, what's the probability that person n comes from cluster k? Well, we can just use Bayes' rule to figure that out. Here I've just written out Bayes' rule is exactly what to expect. It's this probability here. This is pi k. This thing here is just our pk distribution. And to get the denominator, notice we have to sum over all the different clusters. So that's this posterior distribution of what's the probability that Z equals k. That can be called the responsibility. What is the responsibility of cluster k for example n? And we sometimes use the variable r for responsibility to indicate that. And notice that we have 2 subscripts here, responsibility of cluster k for person n. So this is the end of our section on probabilistic models. We defined a whole bunch of probabilistic models, both univariate probabilistic models and multivariate probabilistic models. We need to define all these things, so now we can get to what we're going to get to next, which is kind of the interesting part, which is the learning and inference we can do in a given probabilistic model. So next time, we're going to talk about optimization of parameters, which is to say how we learn parameters for a given probabilistic model given data.